Hello, everybody, and welcome to Symposium 6.0, Artificial Intelligence and Machine Learning. I'm Craig Primer. I'll be hosting and emceeing this event today. Just before we get started, I'd like to touch on a couple of different items. This is being recorded, so just be aware that the recording and presentations will be made available publicly. So if you don't want to participate in something like that, please be aware that this is recorded. Your audio and video have been muted in the audience, so if you have any questions or would like to comment on the question feature on the interface, and we'll see those and ask those and pose those to the panelists as we have time. And then the last thing is, if you have VPN and you're experiencing some kind of lag, it may be because of that. So we'd recommend that you disable your VPN during this session. So to get started, just to review the agenda, if we can look at we'll be moving through looking at the agenda and then turning it over to Curtis. And so again, this symposium is based around resilience, and Curtis will be giving us a bit of an overview on that in a minute. These are our presenters, and we thank all the presenters and attendees today for joining us to go over applications in machine learning and AI towards resilience. So I'd like to introduce Dr. Curtis Smith, who's the Director of the Nuclear Safety and Regulatory Research Division at Idaho National Labs. He's part of the Nuclear Science and Technology Division and sponsors these symposiums. Curtis holds a PhD from MIT and over 30 years of risk and reliability experience supporting organizations like NRC, NASA, and the DOE. So Curtis, thank you for joining and sponsoring this.
Thank you, Craig. And welcome everybody to 6.0. So let's go ahead and get to the next slide and we'll jump right in. So as Craig mentioned, one of the themes that we have and each time we have a theme, one of the themes is on resilience, and we'll talk obviously more about that. But we also have kind of a theme within the theme. If you look back at our previous symposiums, which are online on our AI website at INL.gov, you'll notice this quote about the thing, and AI and machine learning is not the thing that we're after. That's the thing that will get us to the thing. And this is a quote from a television show called Halt and Catch Fire. And so if you haven't seen that, I definitely recommend trying to find that. But and the idea is, what technology can you bring to bear to change the world, really, is what the show was about. And we're starting to see a lot of that, of course, using applications of AI and machine learning. So next slide. In terms of resilience then, that we've had different topics, all of these focused on science and engineering and applications of AI machine learning. The first one we had over a year ago now was pretty successful. We decided to broaden that so we can have a wider impact, and we appreciate all of the contributions from our speakers and all of the interactions and engagements from the attendees. Several hundreds of attendees generally show up for these things, so we're really happy about that. For the 6.0 symposium, that's a typo there, but we're actually tying the talks to what's called Resilience Week, and there's a link there, or you can Google resilience at INL.gov, and still you can register for this. It's a virtual conference that's being held next week on many different kinds of talks related and domains related to resilience. So definitely, if you get a chance, check it out and try to participate in some, if not all, of the activities that we have going on next week. Next slide then. Just a little bit of what resilience is and why that's important. Of course, that's the theme here today, but resilience is becoming more important. It's already important, but more important across multiple domains. And I stole a picture from one of our websites related to the Resilience Optimization Center activity that we have. And you can see, different sectors where resilience is a key to being able to do the right thing for the general public and population society at large. And so if you want to know more about what we're doing on that specific topic, definitely, again, go to the resilience.inl.gov website and reach out if you want to understand more or partner or get more information related to this outside the machine learning AI kinds of activities. But today we will focus on and have multiple speakers on resilience. These will be largely centered on engineering, science kinds of applications, but some interesting topics that we'll see. So next slide, please. And so I wanted to kind of shift this a little bit, getting away from, say, maybe an engineering domain and move into resilience in terms of humans. And just to talk about some of the grand implications that AI machine learning has in terms of, and this example related to what's called protein folding, or ways to really understand how proteins come about, how they could maybe interact with each other, interact with drugs, and so on. So there's a lot of implications here in terms of human health and resilience for people. Again, not engineering of systems, but in terms of folks and their health. There's a benchmark that this community of practice has every couple of years, called the CASP. I've showed the plot of the best performing technology over the last several years. And you'll notice something has happened recently since 2014, 2016. It was kind of a plateau of, how good could we get in terms of understanding how proteins behave and work and making predictions on these. But some new technology has hit this problem space, and that technology, of course, is AI machine learning driven. And you can see all of a sudden, out of this plateau, we're getting close to not quite 100%, but obviously that curve is going to have to bend over at some point, because you can't go above 100% perfection in prediction. But all of a sudden, we're able to effectively run a computer that is almost as good as just simply running physical experiments on these proteins to understand them and understand how they behave, understand the shape, and so on. And so it's essentially a leapfrogging technology that we have seen now in the last couple of years for a problem that has been around for many decades. And in fact, for example, the AlphaFold 2 technology that was the winner of the last go around has been able to do things like experimentalists have gone back, used this new technology to reevaluate their experiments, and have discovered errors in the experiments themselves, and had to redo the results really of the experiments, because the prediction was actually better and actually more correct than their interpretation of the experiments. So definitely a new time for, in this case, drug discovery and proteins. Next slide. And then the thing, once it's okay to have this technology, but really the thing is, how do we change society? Next slide. How do we make a difference? And so the thing really is, can you go back one slide? A little bit of lag there. How can we make an impact with the technology that we have? And that's really, again, the thing that gets us to the thing. And so in the case of the AlphaFold, the source code, the approach, the discoveries coming out of that, a lot of that is just being released to the world as open source. And so all of a sudden, we're able to make everyone essentially a world-class researcher for protein folding. And so that's going to get us to probably a whole new level of health, a whole new level of drug discovery and automation, and so on. So it's a grand time to be able to take this kind of technology and move it into, of course, our domain, which may be science, engineering, complex systems and so on. And so you'll hear a little bit of that today in the next following speakers. And that's all I have today. So Craig, I'll turn it back over to you.
All right, thank you, Curtis. Definitely appreciate the intro and your support sponsoring this symposium series. It's just such a fantastic opportunity for us to bring the community together and hear about relevant topics and see research results. So thank you, Curtis. All right, so moving on to our kicking us off today is who's going to be presenting the AI for energy system resilience. So Liang, if you'd join us, thank you, sir. Liang holds a PhD in electrical engineering from Texas A&M. Congratulations against Alabama, by the way. And managing director for the Stanford Bits and Watts initiative. In this role, Dr. Min leads a multidisciplinary research team in enabling digital transformation for the 21st century electric grid. So welcome, Liang. Appreciate you joining us, and please take it away.
Thank you, Craig and Curtis, for the invitation, and very glad to join this event. And as Craig mentioned, my background, I'm an electrical engineer by training, so I don't claim myself as an AI expert, but I have a privilege to work with many of my colleagues at Stanford. And what I'm going to do today will be, we'll have 3 parts. The first, maybe like 5 minutes, I'm going to share with you some of the recent activity we did partner with the Electrical Power Research Institute, some lessons we learned from that. Then second is I'm going to present some of the work that's done at Stanford, or we are doing at Stanford, and with the team members are listed below. And last, I'm going to kind of call our action. I see a lot of participants from different labs and from different industry. See, give some thoughts of 1 or 2 ideas in how we can work together to really move this forward. And actually, I submitted this slide deck, I think last Friday, maybe, or Thursday. And actually, right after I submitted this slide deck, I realized that every year that Nathan Benich and Ian Hogasa, they publish a report which is called the State of AI to really examine the cutting edge research. So yesterday, maybe the day before yesterday, they just released this year's report. And, they have 5 bullets. And the number 1 bullet is organizations are starting to really trust AI to run critical operations. Not just trim the cost, improve the sales at margin. They use the retailing industry as an example, but also I do see the trend that in the energy system, in the energy sector, especially in the sector that I have been involved in the electricity sector, we do see many organizations, utilities, they start to use the AI to run the critical operations. Okay, before we deep dive into this topic, I want to I realize we have a different sectors here and from the agenda. So in the energy sector, we quite often, especially, my previous life with National Lab as well. And in the National Lab system, we use quite often, which is the PPD 21 and definition of the resilience. Basically, is how we prepare for and adapt to the changing condition and withstand and recover quickly from disruption. That's our definition of resilience. Next slide, please. So this is a recent published report from the Government Accountability Office. Talk about the electricity sector resilience challenge. Basically, they mentioned that the climate change is expected to have far-reaching effects on the electricity grid. That could cost billions of dollars and could almost affect every perspective of the energy delivery system, the grid. And people remember the earlier of this year, the Texas event, what happened in California last year. And it's from generation, from transmission, from the distribution. And because the system we have is on an early stage of once-in-century transition. And we see more and more renewable delivered. But in the meantime, how we ensure that the system is reliable, system also resilient to the extreme events. And also we can provide affordable electricity to everyone. This is really critical time for where we are living. So what we did with EPRI in the last more than 6 months with a lot of national labs involved, including Idaho and several other labs like Unreal and others, is to have a series webinars and brainstorming session to really discuss what are the ground challenges, utilize AI for energy sector, utilize AI for electricity sector. So the ground challenge we identified for the resilience topic, which is, how we can identify, develop, demonstrate, and also really scale the adoption of AI that can help predict weather, demand, generation, electrical grid condition, then continuously use different AI technology to optimize the system to minimize the unplanned outage, but in the meantime, be able to control the electron to flow to the direction we want to flow to. Next slide. So the next slide, which is I'm going to share with you, is couple other ground challenges we learned over the course of the 6 months partnership with different organizations. Next slide, please. So all the information are publicly available and recorded. You can find this at the Bits and Watts website, or you can find it at Electrical Power Research Institute, previous slide, please, website. So basically, the 5 ground challenges we have identified, could you go back to the previous slide? One is the energy system resilience. Previous slide, please. Very good. And is one of that. And the second is how the infrastructure can interact with small communities, smart communities. And the third one is really the decarbonization, the environmental perspective. I think we can stay here. Let me just quickly verbally go through the ground challenges we identified. The decarbonization impact. And the fourth one is really the intelligent and autonomous power plant, including the nuclear power plant and other, renewable power plant controls. And the last but not least is the AI enhanced cybersecurity. We also identified the 3 key enablers. The first one is we realized that, in the last 5 years, the energy sector has tried different AI technologies, and a lot of pilot projects going on in the energy sector. So really the enabler is how we can move the AI projects from pilot to real enterprise production. And the second one is the energy sector has a lot of data. So we have different kind of data sensors plugged in different places of infrastructure. Some of them like SCADA-based, internet-based, etc. How we can really derive the value from massive data we are receiving. And the last but not least is the workforce issue. How we can build a high-performance data science team, either inside the energy sector, or how energy sector can leverage the workforce outside of energy sector in the computer science or IT company to help them on this transition. Okay, and this slide I want to mention 2 flagship projects we just started this year, and it's jointly funded by us, also by Stanford, another institute called Human AI, and also a national lab. And the left-hand side project is focused on the topic about decarbonization and also energy equity. The right-hand side project I'm going to give a little bit deep dive is about how you ensure that during energy transition, how we ensure the equitable and the environmental justice, how we ensure the affordability, how we ensure the resilience, but also how we ensure that 24/7 carbon-free energy infrastructure we're going to have. So I think the next slide will have a little bit of trouble to control. let's see how we can manage it. Okay, there's embedded animation there. If you can click the button, very good. So I want you to pay attention to 2 years. 1 year is just passed, which is 2011. Another one is 2018. And especially on the right-hand side, which is called the heating degree days. And which means that the winter. And on the left-hand side is cooling degree days, which is the summer. Okay. Then the y-axis is the daily demand and in gigawatt. So if you can repeat this video after it's done, then people can kind of observe what happened again. Pay attention to the highest demand across the last 10 years. Second, pay attention to the right-hand side, 2011, and also 2018. Then the third one, pay attention to the last, to what just happened in 2021, the winter. Okay. So basically, what we observed is Texas system is a summer peak system. So basically, the left-hand side graphic has the highest demand over the years. And also the trend is getting higher and higher. The peak demand is getting higher and higher. And the second is in 2011, 2018 winter, what happened in 2021 February, actually it happened before. Okay. So in the 2011 and 2018, Texas also experienced extremely cold winter, but not that extreme compared to the 2021. So if you can go to the next slide, we will see some very interesting correlation. For if you click 2 more buttons, you can see everything together. Okay, very good. And this is the left-hand side is 2018 data. So what we draw the correlation is the heating in the winter, the heating degree days on the x-axis, and the y degree days is the peak demand. So you will see a linear correlation between the heating degree days and also the peak demand or the infrastructure sensitivity, so-called. So it's relatively easy to predict that in 2021, what happened in the 2021 winter, it's relatively easy to predict that if the heating degree days more than 40 or 45 or close to 50 days, we are going to experience extremely high peak demand in Texas system. Okay, so based on the near missed year in 2018 data, so we can predict something in 2021. But it's easy to see we can predict. It's really tough to do that. And what is the missing puzzle in this experiment? If you can go to the next slide. So I'm going to share something that this team, and led by Professor Arun Majumdar and Ramda Jacoba and Andrew N from Computer Science, and Ines Azuduvo from Engineering Resource Center. They work together with a bunch of students to come up with a framework. What we try to do is, on the left-hand side, we have 2 modules. The one module is we're going to work with different national labs and the NOAA and the NASA to really, derive from the climate data to extreme event scenarios. Then our internal, for the last 5 years, we have been developing our AI-driven energy atlas. I'm going to share with you a little bit information later. And the energy atlas be able to, without use any proprietary information, we can map out the whole United States energy infrastructure, especially for electric grid and natural gas systems. And then we were going to come up with these 2 information together to really evaluate what are the supply and demand risk. If we do have a risk, do we have any redispatch alternatives available? And if so, what is the consequence of additional emission may cost. For instance, if we have to utilize more natural gas, and because United States in reality have 40% natural gas are used for electricity, and if we have to use more natural gas in extreme conditions and ramping up the natural gas production, and what is additional emissions are going to create. And then, if we utilize all the redispatch solution, we still not be able to completely prepare for the condition. And what other community will hit the most? Because what happened in Texas is the data we collect is the disadvantaged community or low-income community, they hit the most. So we also develop we incorporate social data science, also develop the deep learning algorithm for environmental justice. So we're going to derive the information that which community are going to hit the most, and we'll feed back this information, go back to redispatch algorithm, also feed back to the infrastructure enhancement or hardening, more on the planning stage. Next slide. So the last slide was kind of overall framework. Then if we deep dive into the specific component, and we see many colors here, and I want to mention that the blue building block are the method or the algorithms or software already utilized by the energy sector, by the electricity sector. Because in the last century, a lot of engineering projects are built based on modeling simulations. We use modeling simulation for airplane and for the infrastructure development, for almost every critical infrastructure we are planning, or we are building, and we are operating is based on modeling and simulation approach. Okay, and in the electricity sector, in the planning stage, we utilize a lot, which is a climate information, and especially for if you build a transmission line, it would be there for 30 years or even 40 years or even longer. And Idaho National Lab, famous for nuclear, if you build a nuclear power plant, it will be there for 40 years, sometimes life extension 50 or even longer. Okay. Then another is we also have the near term is the weather prediction. We use the weather prediction very often, and for the next day, next week, or even next couple of weeks, for the operational purpose, operations and operational planning to prepare that, which transmission line are going to, the storm are going to pass this area, and etc. And the missing part is really something between the climate, which is a 10 years or 50 years, even 100 years, and the weather, which is like a week or 2 weeks prediction window. What we really need is midterm. What's going to happen in next quarter? What is going to happen in next year or next couple years? And another missing part is really how we can derive the combination of weather information, climate information for extreme events, what is going to happen. Then we use this information really help pre-event and post-event prepare for the adaptation for the resilience challenges. And then in the middle part, the green part, very often we have a different sector in the energy space. One is, electricity sector, natural gas, and transportation, etc. And very often they don't talk to each other. They are operating completely different markets. We just had 2 weeks ago. We just had a virtual panel talk about the sector coupling issue. And for instance, the electrical grid, we have energy market, which is we have a day-ahead hourly market, and even we have intra-hour market. But for natural gas is very stable. It's only every day has its price. And also natural gas, they're not like the wind and the solar, the ramping up and ramping down very frequently. But the system we have in the United States, 40% of electricity are generated from natural gas. Then the wind and the solar, the intermittency are going to rely on the fast ramping of natural gas to help them out. Okay. So the sector coupling, the green part, is also something that we're working on. And on the right-hand side, if we consider all this information together, what we do well in the last several decades is, one is reliability, second is the cost. We are able to evaluate the system reliability really well. We are able to evaluate what is the most cost-effective way to build the infrastructure, to operate the infrastructure very well. But the missing parts are three. The first one is how we ensure the equitable transition for this energy system. Second is, besides reliability, how we can ensure the resilience of the system. And also the third one is how we can consider the decarbonization into this energy transition system. Next slide. Next slide, please. So in the next 5 or 6 minutes, I will give you a couple of small examples what kind of AI technology we used for the kind of purpose. So the first one is Atlas, is a project that we started about 3 years ago, and really mapping out the energy infrastructure we have in the United States. The first product we called is called Deep Solar, and basically the team utilized the Google satellite image to map out the whole United States rooftop solar installation. Okay, the team trained the machine learning algorithm, and it's called Deep Solar, to identify the deep solar panel, and based on close to about 400,000 images from the Google satellite image. Then each of them cover about 1,000 by 1,000 feet size, and each image was labeled either having rooftop solar or not having rooftop solar. And from that, the algorithm learned to identify the features associated with solar panel, for instance, like the color of the image, the texture, and the size, and to determine where the solar panel. They found about 1.5 million installation across the United States, which is much higher compared to the two widely known Department of Energy and some other national labs database. Okay. And more importantly, and the team also integrate this information with the U.S. Census information, be able to identify the solar catalog and to see how about low-income communities, whether or not they are adopting solar or they are not, and what's the correlation between the solar installation with the income and with other type of information. So what the team is working on right now is for the solar, for the wind, and also for the hydropower facilities. They use different type of data, satellite image, Google Street information, near-infrared information, and OpenStreetMap, and to really map out all the critical infrastructure. And next slide. Another example I'd like to give to you is they use the combination of a satellite image and Google Street data to analyze the underground rate for the power line in the state of California. So in the left-hand side are very interesting information. The x-axis is the median income data, and the y-axis is the underground rating. So you will see, the low-income community which has a extremely low underground rate, but it also has a cap to kind of $200,000 income. Then after that, it's going down. It's because rich people like to live in the forest. They don't want anybody to bother them. Right? And then on the right-hand side, you will see full picture income, the housing density, and the wildfire probability in the next 30 years, and also the distribution grade. It's basically the power line undergrounding rating. So, I highlight two areas. One is the area, which I am right now, is the Bay Area. We have a little bit high wildfire probability, But in my community, and all the lines are buried to the underground. But another community is very famous, like Yosemite. A lot of people may be there or travel to there for vacation. And they also have very high fire probability, but the underground rate is very low. Okay, so basically, this is another example, how we use a satellite image, a combination of Google Street data, and to derive the information about how resilient are the community against to the wildfire. Next slide. Next slide, with the time very quick, is we last year, with the beginning of the pandemic, we spent almost like 6 months or longer collect more than 50 countries' electricity utilization information. So in the right-hand side, you will see, from February 2020 to June 2020, and different regions like North America, South America, Asia, Europe, and the color indicate the load reduction over the time. Okay, so we'll see like February last year, China hit the most, then it's moved to South America, then go to Europe, like Italy, then go to India, and really about April and May timeframe last year, a majority part of the European countries and Asia and the United States are hit by the COVID-19. But the more interesting is after that, after April and May, and how the economy and the demand are recover. So that's what we plot in the left-hand side. Each blue line indicates one country, and the black line is a mean value for the system. But this gives you the information, the risk of the supply and demand, and also how fast the economy can rebound after extreme events. Next slide. So with the last two minutes, I'd like to call an action. It's what we learned based on the conversation we had with EPRI and many industry. And so every time we talk about AI, the number one challenge is a data challenge. And utility and energy sectors, we do have data, but the challenges is how we can create an industry-wide data sharing mechanism, because we are operating critical infrastructure. For example, the transmission system, we call the critical infrastructure, critical energy infrastructure. A lot of data cannot be shared with a very certain approval and etc. And also how we can create a governance mechanism to ensure that data can be shared with research communities, but also can protect the security and the privacy of a different type of data. And the last but not least is the tons of very valuable information, public available information available. How we can help the energy sector to utilize this information to help them to make either hardening decisions, investment decisions, or operational decisions. I've been giving several examples like the weather information. We have been using that for a long time, the satellite, the census information, the social cost, etc. So last slide is a quick example we are doing. We are partnering with an organization called Data Common, which is a non-for-profit division at Google, and create a common infrastructure and to share the public available data, but also be able to leverage and govern some of the proprietary information, offer this one to the community, both the research community and also industry community be able to leverage the value of the data. With that, I'd like to conclude my talk. The key message I want to deliver is there's a lot of opportunity. Let's work together and digitally transform the next century of energy system. Craig, back to you.
Thank you so much. Appreciate that. Very interesting topic. So thank you for sharing your results and your perspective. So thank you. All right, we're going to be transitioning next to Vivek Agarwal. Dr. Min, we don't have any questions for you right now, but if we do, and I'll remind the audience, if you have any questions for the presenters, please feel free to pose them. If we have time, we'll answer them real time. If not, we'll get them sent out as part of the package of information of this symposium. So thank you, Dr. Min. All right, so transitioning now is Vivek Agarwal. He's presenting the resilience of federated transfer learning. So Dr. Agarwal is a senior research scientist at INL and leads several research activities, including the INL's Fission Battery Initiative. Vivek's research specializes in developing cross-cutting applications and advancements of sensor technology to enable resilient real-time measurement and control of process variables within nuclear and other infrastructure or industries. So thank you, Vivek, for joining us. I'll just mention to the audience, we have some longer presentations, which we just heard, and some shorter presentations. This will be an overview presentation of Vivek's work. So thank you, Vivek.
Okay, thank you, Greg. I hope you can hear me okay.
Yep.
Okay, thank you. And thank you for the organizers for inviting me. This work, what we are presenting here is a team effort. It's a joint collaboration between Idaho National Laboratory, PKMG Technical Services, which is part of Westinghouse, and PSEG, Public Service in an Enterprise, which has a nuclear entity. Right? Next slide, please. So what we are basically tackling here is transforming, as Dr. Min has spoke about the energy system, we are kind of scaling back and going to the energy generation side. So, and very specifically on the nuclear side. Right? Within the nuclear current fleet, there is a huge transformation and is happening by using digital technologies and AI to go from what has been a periodic labor-intense maintenance strategy to a technology-driven AI condition-based maintenance strategy. When we do this transformation, there are different elements that we need to take into consideration, and not only the system upgrade, but also the organization adaptability to this transformation. But in this presentation, I'm just going to focus mostly on the pipeline that we are taking and going from where we are integrating an AI-driven predictive modeling approach with risk modeling and visualization. And in previous presentation, we saw the power of visualization. There are some valuable information so neatly presented visually that it's easy to understand and respond to. So that is one of the attribute of the resilience is how do you respond, recover and respond to a situation. And so that is a big focus here. And Dr. Min also led very importantly towards the end. Biggest piece of any predictive analytics is data, and the data are available in a different form, different resolution with different entity, and data sharing is a critical bottleneck that we need to address. But there is a different perspective that we would like to share here is like how federated transfer learning could have can present an opportunity to address that issue without having a data common or data lake, where one entity kind of collects all the data or distributes the data. Next slide, please. So one of the things that we are looking here is on a motor-driven pumps. So very specifically in this case, we are looking at a vertical motor-driven pump, which has, and you can see from the schematic, has different data modalities, and it contributes to the plant operation, which is reflected on the top right with the gross load. Basically the amount of energy that the nuclear power plant sends to the transmission unit. Right? And these data are collected on a different time scale and at different and using different instrumentations. So that creates another kind of scalability and data format issue. And now next slide, please. Now, how do we address this challenge? And so this schematic of federated transfer learning is kind of an overview. It's a big overview here that we are giving for the federated transfer learning is On the left side, you can see the federated approach, and you can see that there are vertical motor driven pumps, but these pumps could be across the fleet, across the plant site, right? But on the other side, you can replace these vertical motor driven pumps by different entities, like what Dr. Min showed. The transmission might have their own data, housing might have their own data, the different generation system might have their own data. So think them as entities, each motor driven pump here as entity, and they collect different data: vibration, climate, economic data, work order data. So all this data, and so we can, instead of sharing the data, we can say, yes, we can build a local machine learning AI predictive model using the data that is available at that plant site, or at that housing sector, or at the transmission unit, and just share the data information and model information and to a centralized service. This creates the kind of one-way addresses the issue of sharing the data, and also data privacy issue. And once this data is transmitted to a centralized server, you can be aggregated to develop a master model, which could benefit from the diversity of knowledge that is going to aggregate and transfer it back to the entities at the bottom. That's a part of the federated learning. On the right side is the transfer learning. Sometimes you bring in a new entity, or you transfer or you go into a different sector here. Instead of rebuilding everything, you can start with an established baseline model and it can adapt it later. So that's part of the transfer learning. So that is the biggest aspect of federated transfer learning. Next slide, please. So here is the aspect of that we think the federated transfer learning brings to resilience. It minimizes the impact of sensor or data loss. So as I mentioned, that each entity on the federated side can have their own sensor set of data, or its set of sensors. And even if they have same, say in the case of vertical motor driven pump, if you lose one vertical motor driven pump, you're still able to adapt to that situation. And even if you lose few set of sensors, your model is not going to be impacted, lost much, because you have a global model that has taken into consideration the benefit that has already been aggregated by when the data was available or when the asset was available. I've already mentioned about data privacy. You don't have to share the data now. The data is with the entity itself. All you have to do is to share the model parameters. So that creates a kind of also a cyber resilience. And if you want to transfer the data, you have to think about what kind of communication architecture you need, what kind of data infrastructure you need. So that issue is kind of little bit addressed by federated transfer learning approach. It ensures scalability. When we talked about scalability, here we are ensuring that the model that we develop for a particular asset in a nuclear power plant can be scaled to different assets in the same plant site or across a fleet. But however, if you replace the bottom half with entities, the information can be scalable across entities. The third part is a variability in operating conditions. Suddenly, if you bring in new information, that is something what Dr. Min showed about the change in the weather pattern and demand in Texas. And that's a variability that machine learning models or predictive models need to adapt to. And this way you can bring in the adaptability with the federated transfer learning. And the last important concern that we want to share is resource constraint. So each entity, if you think, might have different level of resources available. Some might have a high computational power requirement, so they can do crunch a large volume of data. Some might not have, and some might do the upgrade every day, some might do every month. So that is a resource constraint that still can be addressed by this federated transfer learning approach. So that is and by providing this kind of aggregation of salient features and information, what you're preparing your AI model is not one to respond to any adversarial event, and either in real time or in anticipation. So that is a research that we are working at Idaho National Laboratory using the federated transfer learning. Next slide, please, and which is probably my last slide. And I would like to acknowledge the team here. As I mentioned, it's not it's one person's effort or one entity effort. It's a collaborative effort, and it's funded by the Light Water Reactor Sustainability Program. And with that, I'll turn it back, Craig.
Okay, thanks very much. Appreciate that. And we definitely have seen a lot of need for that type of approach with the as we're engaging industry and their questions around what would happen and how would you respond to losses of sensors and different things. So definitely a good thing to understand and for people to start to consider. So I'd recommend anybody interested in that information or learning more about that, getting in touch with Vivek. So thank you, Vivek.
Thank you, Greg.
All right, so next up is Shar Samples. So Shar's going to be providing insight into building resilience into AI/ML. Dr. Shar Sample is a cybersecurity principal at Modern Technology Solutions, where she currently supports a research and engineering directorate for the Office of Secretary of Defense. Presently, Dr. Sample is continuing her research on modeling cyber behaviors by culture. Other areas of research are data resilience, cyber physical systems, and industrial control systems, including trustworthy artificial intelligence research. So welcome, Shar. Appreciate you joining us.
Thank you, Craig. Good to be here.
Yeah.
I take it everybody can hear me okay and see me okay. So
You can, yep.
okay, so I know I only have like 10 minutes and we're one in already. So next slide. Some of you are familiar with, so we'll just make sure that we're on the same page learning-wise with AI, technology that performs tasks which mimic human intelligence. We have different models that we use to model human intelligence, such as heuristics, trees, neural networks, things like that. We have not yet figured out how to move between the different models that we use, that we seamlessly move between. And that's why human cognition and things like that, behaviors become of interest, because ultimately this is going to feed into how we interpret and organize our our machine learning training data and come out with our insights. Machine learning, this is what powers our artificial intelligence. Algorithms are capable of generalizing lessons learned from small sets of data and able to allow for the abstraction into for a larger environment. And we've earlier heard that sometimes we have to go back and get more data, reinforce our learning, so to speak. And that's normal. I mean, we don't learn everything all at once in our lives either. We apply things and then we kind of learn from our mistakes. And this is also kind of an aspect of resilience. This gets to our robustness and our ability to adapt and be able to do this physically. As humans, we do this. So now how do we make our computers do this? How do we make our artificial intelligence do this? So I think we all agree this is a disruptive technology. And if it is the thing that gets us to the thing, I'm here to talk today about how do we make sure that we can trust this thing that gets us to the thing. So next slide, please. So some of you have seen this before. These are, to me, the pillars that we need to use to build trustworthy AI. And so we need to build resilience into it through resilient data, resilient systems, resilient models, and of course, explainable AI. When we talk about resilient data, we're talking about being able to determine if our data has been poisoned or if we're looking at it wrong. So it's data that's bound to its environmental variables so that we can determine if this is normal, baseline data. I was really happy to see that there's a group out of the Naval Weapons Center that is actually has an initiative to baseline a lot of data and to baseline systems for use in artificial intelligence, because if we don't get the baseline right, everything else, I don't care how good your algorithm is, it doesn't mean anything because you've learned the wrong lessons and you're going to come out with the wrong insights. When we talk about resilience in general, there are 4 R's to resilience that we like to talk about. We talk about robustness, resourcefulness, redundancy, and rapidity. And so when we're talking about how we do this with data, how do I make data gather these 4 R's? Well, the robustness comes from being able to bind data to its environment. The redundancy comes from having certain values in there that you basically have as other fields and other records, or you have them duplicated. When you're talking about the rapidity, that this is important, that you have some pieces of your data that carry across different fields or different records that you can go ahead and use to rebuild a new record should you need to rebuild or reconstitute yourself. So you need to have like these anchors, I call them, and then you can pull in from the other pieces that you have managed to save. So that's kind of one way you can look at making your data more resilient besides just robust. If we move up to resilient systems, we see that we have things like self-healing systems. We have work that I know Jed Hale was doing on red teaming AI. We have other efforts involved where we have some of Rita's work, Rita Foster's work, where she's actually collecting data on malware and things like that for industrial control systems. So here again, we have the ability to gather things in the context of their settings, and we can now look at the systems in which they're enacting and say, okay, we may have a bad system here. Here's how I can discern this early on. And if I can do that, then I can start thinking about how I'm going to adjust accordingly. One of the more vexing problems we deal with is the models themselves. If the models are flawed, and we have seen where flawed models have become a problem, this is a problem that is very hard to detect because people are able to manipulate how they ask a question, how the questions are answered, the quantities in which responses are given, manipulate quantities and things like that. All of these things don't leave real traces. If you have a bot, say, that's giving a specific response and it's flooding the network with that response, it's not breaking anything. So being able to actually determine that something is wrong becomes a problem. So what we want to be able to do here is be able to start thinking about how do we make a model resilient? And this is actually kind of a challenge I will be talking about with James LaRue next week at Resilience Week. So a little teaser here while we're going here. Then of course, above our models, we have the ability to explain what's happening. And even though it's not as exciting to a lot of people, the need to understand how we make our reasoning with our cognitive process is really what feeds how we model artificial intelligence. So what I want to understand is how do you take the electrical signals of the human brain and actually take that and make software from that to understand what model we use when we're trying to solve a problem. If we have all of that together, then we have something that we can not only trust, but we have these resilient components underneath it that say that even when something goes wrong, we can still count on it to do what it was originally intended to do. And with that, I believe I have, I'm going to say next slide. And these are some of the things that we look for when we're trying to create resilient data as well as systems. And I have the slide labeled data, but I thought about, we can pretty much, this applies to many of the other areas too. If we slide down, because I've covered the model at each level, so next slide and then the slide after that, we will see for resilient systems what we do. Oh, okay, 3 slides. Keep going. There we go. So back one. And if you see on a resilient system, you saw that here we look for robust software, hardware, things that can withstand an attack. We're looking for redundancy in our supply chain, also resourcefulness and rapidity and self-healing. These are the sorts of things that we're looking at to make our systems more resilient. And the supply chain, of course, is a wide open target, but there's, even looking at the hardware itself, we're finding that there's a lot of things that are advertised that are happening in hardware that we haven't really shown that that is indeed the case. So that's why these baselining initiatives are so interesting right now to some of the folks in OSD. Okay, next slide. We'll I think it's like 3 more slides we're going to go up, and then we'll see where we have resilience listed for the models, and I'll open it up for questions. There you go. So here we go. For the models, fingerprinting, countering fingerprinting efforts, temporal analysis. One thing that we do want to do that's true of when we're dealing with resilience in models, we can recognize that people will try to exploit our models. So what we want to be able to do is enforce Byzantine behavior, and another area of research that I believe Matt Bishop was doing is what we call inconsistent deception. So we know that somebody maybe has is trying to manipulate our artificial intelligence. So can we give responses that will confuse them? So I know that this was a little disjointed, and I only had 10 minutes. So any questions, I'm happy to answer. Thank you, Craig.
Yeah, thanks so much. Appreciate that. I know, part of what we're trying to do here is get a lot of information out for people to become aware of and who's working in that space, and connect people with like-minded interests to start collaborating. So I know it was a lot to get done in 10 minutes, but really appreciate the introduction of the topic and your ideas around that. So thank you, Shar.
Thank you, Craig.
You bet. So we'll be moving next to Craig Rieger. Craig, if you could join us, please. And thank you, Craig, and thank you, Shar. So Craig is going to be discussing the foundations of resilience, and specifically the transformation of cross-disciplinary collaboration in dialogue and tools. So Dr. Rieger is the Chief Control Systems Research Engineer and a Directorate Fellow at Idaho National Lab. Craig is also a senior member of IEEE and has over 20 years of software and hardware design experience for process control systems, upgrades, and new installations. Currently, Craig is leading pioneering interdisciplinary research in next-gen resilient control systems, providing integrated research strategy to address complex control systems, cognitive cyber-physical challenges into self-aware, trust-confirming, and threat-resilient architectures. And I had to boil down years of experience into that, and I could have gone probably 20 minutes on Craig's background. So welcome, Craig. Appreciate you joining us, and I'll turn it over to you.
All righty. Well, thank you, Craig. One of the few people with the same name that I actually have to watch out for, because I'm so not used to it that when I hear Craig, I turn around thinking somebody's talking to me. So it's good to have you on. And thank you, Curtis, for inviting me. And so what I'm going to talk about today is really how I wrapped my mind around what started as a cross-lab initiative to develop areas that we were already really developing: cognitive control, cybersecurity, but recognizing that, if we want to fundamentally change things, we have to achieve resilience. And fundamentally, that discussion is many others. So if you join Resilience Week next week, I have a short plenary. It's going to sound a lot like this. There are some differences, but there's going to be people like David Woods. David Woods is a cognitive psychologist that's been working in this arena since the 90s at least. And he believes that we don't even have a lot of the science. So just talking about interdisciplinary aspects isn't enough. But suffice it to say, it's very much about what I've been about, that the technologies are an offshoot of developing the discussion. Even between engineering disciplines, we use different nomenclature and things like that. So how do you develop the discussion to address the challenges? And so I will talk about resilience in terms of resilient control systems. Obviously, it's much broader than that. Resilience Week has community resilience, infrastructure resilience, in many areas that are somewhat disciplinary focused, but that was really all about developing that dialogue. So to start with, to look at what I believed was the foundational data to suggest what we focused on resilience, we talked about control system complexity. So from a control system complexity standpoint, these systems have been organically developed for decades. The earliest control systems I know of that were digital started appearing in the 60s as custom aspects. 70s, PLCs came out. 80s, distributed control systems came out. In 90s, you saw some of these systems getting into more open systems, and capabilities that you saw in DCS crossed over to PLC because, of course, control system vendors wanted to sell to whoever they could. And even though you had new systems out, you didn't necessarily replace the old ones because they work. So, okay, well, we'll just interface them. And as you saw, different issues come about that were concerning to you, such as we've got this discharge blower that's pulling a vacuum on all these facilities. And if we have to shut down something for maintenance, shut down those blowers, there's still ventilation going out to the stack. As long as we shut down the supply blowers, it's pushing additional flow. Well, that's with a different group of people, different control system. We'll put an interlock in there. Well, you start adding all these interlocks and interdependencies, and all of a sudden you run into a unwieldy system of different generations of systems, different ties to different parts of the process. And even if you have good documentation, people make mistakes. And fundamentally, when you've got control loops that are doing automatic things, I'm not going to say autonomous because we're really not to autonomous systems, even though vehicles have been moving that way, and they have them. There's still challenges. And so, how do you address that complexity so that the systems are resilient, so you don't end up with a Swiss cheese situation where all the holes line up and all the things you thought were preventing the problem don't stop it. Next slide, please. So then we add cybersecurity, and control systems didn't used to really care about them. I mean, they didn't even have anything but proprietary networks. They were disconnected, and then, well, we want to get the control system data, so they started connecting them, and then they started using open system architectures or standard control system commodity protocols based on IP, and all of a sudden there's connectivity at the consoles, and they said, well, yeah, we want to use that also for the communications between the human-machine interface and the controller, so they added it there, and pretty soon the standard footprint and the exploits started moving that way. But what we've seen even in the 2000 and years that followed are exploits that have come out specifically for control systems. Why? Because they control the stuff that matters. Now, yes, we don't want to lose our stock accounts, and so finance is very important, but you start thinking about the power, the water supply, and everything else that's run by control systems. And what we've seen is a lot of these exploits continue to build upon themselves. Not everything is brand new. Unfortunately, we only know what we've seen. But now people can get into the game that aren't necessarily experts and do bad things if you don't have protection. And so really what we're looking for with resilience is cyber resilience. And I'll talk about that in a bit, but it's really moving towards what we do in control systems, which is more understanding of what kind of failures we have. Is it malicious or benign? What's the problem? And also then doing a response at machine speed. But in the middle is still a human. So there's a transition that's going to be necessary going forward in that. Next slide, please. And so finally, in talking about human system complexity, I'm guilty of throwing too much information, or should I say data, at an operator. I did control systems for 20 years, used to configure a lot of the graphics. We let the operators configure the graphics. We brought in human factors people to make sure we weren't overusing color, we weren't overloading the system. There's an evolution there. It's a very important evolution by the cognitive psychologists to really understand how to present information. I did smart alarming in the early days, which means instead of getting 50 alarms that indicate one problem, that you've got one alarm that indicate one problem and a response. So even back in the 80s, we were doing that kind of stuff, but it's got a long ways to go. And right now, all we do is present the physical information. And if we're really good, we present some analytics and decision support, power systems, transmission in particular. You see quite a bit of that, but what about the cyber? What if the impact cyber? We're going to show that to the operator? Well, that's a different response. And guess what? It's not just the physical person that needs to respond. It's a cyber person. And the cyber person doesn't know what's important to you. You may hit a non-consequential part of the plant, or it may be a consequential part of the plant, or both may be occurring together. So understanding that becomes extremely important. And so the new work that I do is actually looking at how to present that information so the human can be effective. That's the first next step, because you also have to have all of those analytics and do it right to be able to do things autonomously. And if you can't present it to the human right, you're not going to be able to do it autonomously right either. Next slide, please. So for us, the definition of a resilient control system is basically the capacity of the control system to maintain state awareness and an accepted level of operational normalcy in response to disturbances, including threats of an unexpected malicious nature. A resilient control system is basically one that counters threats, damaging storms, cyber attack, other kinds of unrecognized complexities. The state awareness part, the first step, which is actually the first step in any control loop, is having enough knowledge to fully characterize the decision space. This is not a physical failure, this is a cyber attack. The response is different. Once you know that, then you have to yield a response. So what is that response? You know, when you're doing things in the cyber world, you have to know what it's going to affect. Things like if you shut off a port using software-defined networks, what did I just screw up that was worse than what I was trying to solve? You need to know what traffic's on there. You need to know what control loops are sharing information. They're very time sensitive. Determinism is the big word. You need to understand that. You need to have different options for how you would respond. Not all of them are totally new. Some of them are actually better using redundancy. So you heard Shar use that word redundancy. You know, better understanding how to use redundancy, what things you may want to have as a controller that's a backup that nobody sees. Many of these things still have to be worked out going forward. Next slide, please. And so when you start thinking about the disciplinary and ultimately the application alignment, I came up with this graphic actually several years ago for another conference or another workshop that I was at that we put on within NSF. And so thinking about the upper left, I mean, what's the value proposition to start out with? That's where metrics are important. People are proposing metrics now. We've certainly been working on that for a long time. We have our own metric solutions. Industry needs to think about things a certain way. They're looking at their own solutions. What is the difference between resilience and reliability? I asked that question one time to some people from PJM, and I was impressed with the answer, actually. They thought about it for a little bit, and they said, well, one of the things that we're thinking about differently is, let's say we have a damaging storm or something like that. We know that we're going to need more human responders, but how are they going to get to work? Or what about the COVID situation? A lot of people are writing about that, have been for the last year plus. They bring in that human element, which is your now understanding is extremely important to me because all humans are different, but they're fundamental to resilience. It's not just about autonomy, and even if it was, that's still a human that creates it. So you need to be able to have a business value, but you need to be able to define it. You know, what are you going to ultimately achieve that's different? For us, looking in, you know, more the upper right corner, there's the cyber physical and the cognitive. So we have physical awareness, you have cyber awareness. You need to fuse the two. We actually do that for cyber. What's malicious and compared to what's benign. Lower left, you have cyber control and cognitive. So in the physical environment, we're doing control loops. We have the physical feedback, but you also need to think about cyber feedback. The cyber response to mitigate, as well as what does the human need to respond to, and making them aware of what the cyber response might be. And then that's where the mixed initiative comes in, because for the technology, the autonomy to be effective, the human has to work as a fundamental part of that. The human's never going to be as fast as the autonomy can be, but there has to be a working together. In the robotics realm, it's the robots being aware and working with the human, the interaction. That term actually goes back a number of years. And then finally, resilient design, state awareness, countering threats. I mean, that's ultimately what we're after. And as we look at this, we're looking at adaptive architectures. We're looking at how to make the architectures for distributed control system, which have been talked about for years, actually distributed. It's not a distributed control system like people sell from the ICS vendors. It's actually distributed control, thinking about how you distribute the recognition and the actions. Next, please. So the notable challenges, potentially in the power system especially, but elsewhere with all that complexity, cascading failures. And we've seen cascading failures, 2003 blackout, other things that have occurred since. What could have happened to Texas? It could have been much worse. And couple that with cybersecurity realms, the fact that control systems are late in the game. And ultimately, you know, for us as researchers, we still need to think about where the systems are, because they're really not going to want to replace everything, even if they had the money, could they? What do we look to get out of it? Well, if we really understand and characterize well our environment, we know cyber physical and resilience aspects of it, we're creating a foundation really for the autonomy going forward. Because if you don't recognize the failure and what it is, and it ripples up through the autonomy, you've got a big problem. And in fact, from a malicious side, that's where a malicious actor would attack and use your autonomy, your complex algorithms against you. That's also why they need to be diverse. They need to be distributed. You look at centralized systems and they can be potentially failure prone going forward. Once you've done that, you can maximize operational efficiencies. You can better use the operator. So you've only have so many humans. If you have damaging storms, hurricane, even if you prep for it, you're looking to prioritize the human response, those things that they need to be aware of, and those things they actually have to send somebody out, the line crew, whoever it is. Can the line crew actually get to that location? Did we place them there before the storm? They know they're going to be protected, but we have a bridge that's susceptible to getting flooded out, you know, those kinds of things. You can use the autonomy to help you if you've got the data and if you've got the right analytics. And that's really where we're heading. And it's the first step. As I said, informing the operator is the first step to the next stage. The next stage being, okay, what can we push to autonomy? We need to make a fast change. I mean, if you look at power system relays, the things they respond to in the transit realm have to be super fast responses. That's why, even back to the analog days, that kind of response was pushed out there and, dare I say, distributed. Next slide, please. So I've done kind of a matchup here of reliable to resilient. And some of this you've already caught from my other discussions, but centralized monitoring and control is rife with potential problems from a resilient standpoint. It's not that it's not right. It's not that it's not going to stay that way. You can't put people everywhere you want them to be. The challenge is if you're doing all of your correlations at a centralized level and you start losing lines due to a cyber attack, storm blowing away your comms or something like that, you're in a bad situation. And we've got many of these complex latencies that just, you know, interdependencies and latencies that underwrite that. If you think about the future of the system, you're decomposing your dynamics. People use the term multi-agent control system. You're actually analyzing and responding at the lower level. It doesn't mean that there aren't some centralized set points or actions that are taking, but those are slower timescale. You're actually acting on information you do have at the lower level, could be at the substation or somewhere like that. And you're also in advance looking at the trade-off analysis. In other words, if I isolate these ports because I see a cyber attack, it's not going to cause something unexpected that the human can't respond to. But you also don't depend on the human always having to be there. There's actions you can take. The important thing in going from what we currently have is there's a multiplicity of goals and different human performance. So providing them the priorities and presenting the information in a way that they fully understand it so that they can be more effective in working with that is really where we need to go. And finally, as mentioned before, malicious action, I mean, that's part of something that affects the control system and the human, ultimately, performance in those kinds of responses. How do you make the roles work together? So there's an interdisciplinary operational aspect that needs to be developed going forward. Next slide, please. So this is just a correlation of a bit of the research areas that we've done that are looking at multi-agent architectures, role-based context awareness for response, trustworthiness assessment. As Shar said, you have to trust the data. And my final slide. Next slide. So this should be about Resilience Week. This is a virtual year. Unfortunately, we had to push to virtual. This is my last year's chair. So we have a large organizing committee that includes multiple labs. This year we've had Senator James Risch, who actually did a great presentation for it, a number of plenaries. Next year, hopefully, will be in person. And thank you very much.
Thanks, Craig. And you know, the timing's really nice for being able to highlight the Resilience Week, and appreciate all the effort you're putting into that. So I encourage everybody to register and attend next week as you can. So thank you, Craig, very much for presenting that.
Thank you.
All right, next up, we've got Xingong Chao, who will provide an overview on machine learning driven prognostics and health management, specifically looking at opportunities and challenges for the nuclear industry. So Xingong has a PhD in nuclear science and engineering from MIT and is currently a postdoc at Oak Ridge, researching areas across nuclear engineering, computational hydraulics, modeling and simulation of complex systems, INC, and then artificial intelligence for nuclear applications. So welcome.
Thank you, Greg. You can hear me okay?
Yes, sir.
Thank you for the very nice introduction, and I'm honored to be here today to give a brief overview of the AI ML driven prognostics and health management for nuclear power plants. Next slide, please. Resilience is about recovering quickly from adversity, and in critical energy infrastructure, adversity can emerge from all kinds of threats like natural disasters, disruptive events, and cyber physical attacks, as well as unexpected equipment degradation or failure, which is the focus of this talk. And for energy systems, the situational awareness is essential for managing asset health and characterizing the decision space. And that is in line with the principles of prognostics and health management, or PHM. Next, please. Resilience is also closely connected with risk and reliability. And in nuclear industry, PHM-enabled capabilities are being developed for predictive maintenance and autonomous operation, especially for advanced reactors, small modular reactors, and microreactors. Such capabilities will significantly reduce the cost of plant operation and maintenance, as well as the reliance on human labor, while maintaining or even improving the availability of nuclear power plants. This cycle on the right shows the iterative process for autonomous operation using PHM, from monitoring to decision making. Next slide, please. So in a nutshell, the PHM framework consists of 5 modules. We use sensor technologies to collect data from the target asset, continuously monitor for indicators of incipient faults and anomalies. Then we diagnose the fault and determine the current health state of the monitored asset, apply prognostic models to estimate its remaining useful life. And finally, results from both diagnostics and prognostics are combined to inform the planning of operation and maintenance and proactively manage failures. Next, please. Among the traditional modeling tools for PHM, especially diagnostics and prognostics, we first have physics-based models that represent the underlying physical mechanisms and encode the first principles input-output relationships. Then we have knowledge or rule-based models, which are built solely upon expert knowledge. We also have statistical-based models that treat degradation as a stochastic process and apply conventional statistical analysis methods to interpret the condition monitoring data. More recently, fast-growing advances in AI/ML have significantly enhanced the PHM applications, from robust anomaly detection all the way to automated control of complex systems. And the AI/ML-driven PHM models attempt to learn degradation patterns and make predictions directly from the available observations using AI/ML algorithms. Next slide, please. This slide actually shows some examples from recent publications about AI/ML driven PHM. So there's a lot of ongoing exciting R&D work in this area, both within and outside of nuclear. So this is definitely not the full picture, but just to give you some high-level snapshots. The upper left pie chart suggests that the data-driven methods, both statistical-based and ML-driven, have attracted most of the research attention in machinery prognostics. The upper right diagram summarizes the different deep learning algorithms that are being used for PHM. So there are many of them. Deep learning is a promising subfield of ML, and this paper actually provided a comprehensive review of the state-of-the-art deep learning-based PHM models. In the bottom left quadrant, we can find a recent ML application in prognostics that use data from the feed water and condensate system of a boiling water reactor, and compared both the support vector regression and the LSTM, which is a recurrent neural network architecture. And finally, the bottom right figure represents a digital twin workflow for the nearly autonomous management and control system that is enabled by AI/ML driven PHM. Next slide, please. So for AI/ML driven PHM, the method development and implementation cost is relatively low because we don't really require prior knowledge of the underlying failure mechanism. Those models can be deployed at any level, from component to subsystem, all the way to system and structure level of the target asset. And they usually perform very well when large volume of multidimensional data is available. However, they do have some drawbacks due to that are inherent to AI/ML, and primarily due to the black box and data hungry nature. And these would lead to challenges in terms of interpretability and explainability. There are other challenges associated with AI that are not listed here, such as scalability, reproducibility, and trustworthiness, as highlighted by the previous speakers today. Next, please. The hybrid PHM models can leverage strength of different model types. One popular direction is AI/ML augmented with physics failure knowledge to relax some data requirement and make models a bit more interpretable. The other direction is the ML combined with Bayesian approach, such as filtering algorithms, for their robustness and their ability to reason under uncertainty. So hybrid models are definitely a desired first step towards more interpretable and explainable AI, but they are not the magic pills here, because they come with their own challenges, such as being computationally expensive, and sometimes their validation verification can be difficult. Next slide, please. So most advances in PHM actually started with non-nuclear applications, and adapting them in the nuclear context may face some additional challenges, the first being data. So there's a growing realization that most of the recorded operational nuclear data are either not publicly available or not useful, not to mention that we are yet to collect any data for reactors that are beyond the second generation. And with AI/ML driven PHM, the effectiveness of our models is unfortunately constrained by both the quality and the quantity of relevant data that are available to us. The second challenge is that the failure modes and degradation processes for certain assets remain poorly understood, especially those exposed to harsh stresses. And this is actually a key need for hybrid PHM development, although in this case, we probably won't require very high fidelity modeling. Next, please. Sensors are critical. Currently, installed sensors in nuclear power plants may not be enough for PHM purposes, especially for passive assets. And optimal sensor placement is very important to ensure marginally intrusive coverage at a reasonable cost, and so is high sensor reliability. And finally, the regulatory requirements for PHM implementation in nuclear are not clear yet. We know for sure that adding any INC and changing any O&M practices for safety-related equipment would definitely need approval from regulators. But instead, the non-safety related assets would be considered ideal candidates for PHM coverage. And also, given current regulations, AI/ML would probably only be used for operational decision making, but not in the context of safety and protection systems anytime soon. Next slide, please. And this is my final slide. I'd like to wrap up here with some potential solutions to fill the gaps. First, in terms of data, we call for integrated model building and data collection efforts through some sort of benchmark testbeds and a roadmap for industry-wide data sharing led by DOE and industry. We definitely need more in-depth R&D on data and physics integration for hybrid PHM models, address those AI challenges, and make it more interpretable, explainable, and trustworthy, using methods such as transfer learning, federated learning, meta learning, and also develop new inspection and sensing techniques for advanced nuclear applications. And last but not least, we need a robust and unifying assurance framework to ensure that we can evaluate our PHM models by means of validation verification, nuclear applicable standards, as well as uncertainty quantification. And that is the end of my presentation. Thanks for your time.
Thanks, and that's a nice summary of the areas left to do. So thank you very much for your presentation. Okay, next I'll be introducing Parati Ate, who will be providing an overview of resilience-friendly features in NMAC. So welcome. Oh, I'm sorry. I think I got a little ahead of myself there. So yeah, Parati. Let's see. I think actually I should have introduced Roberto next. Sorry, Brady. We're excited to have you, but you're the next one. One more. So I'll invite Roberto next. Sorry for the confusion. All right, here we go. Back on track with the agenda. So Roberto, thanks for joining us. So Roberto's going to be providing an update on explainable and trustworthy diagnostics achievable through process-based automated reasoning. Roberto is a principal nuclear engineer at Argonne and received his PhD in energy and nuclear science technology from the Politecnico di Milano. Sounds like a nice place. His research activities at INL are mainly focused on development and diagnostic algorithms. Sorry, need some water. Algorithms, design of control systems, architecture, and semi-autonomous operations. So welcome, Roberto, and look forward to your presentation.
Thank you, sir. Can you hear me okay?
Yes, we can.
Perfect. Okay, thanks everybody for joining. Thanks for this opportunity. And you know, today in this 10 minutes, I'm gonna give it a try to provide an overview of this automated reasoning approach that we've been developed at Argonne in the last few years. And so please, next slide. Okay, sweet. Okay, so the concept of autonomous operation basically is a new dimension of opportunity to improve cost competitiveness and nuclear power. So the idea here is that there are other industries, aerospace, transportation, space, have targeted autonomous operation of a means for cost reduction, and they've already seen commercial inroads. So the plan is, let's try to leverage their experience, their efforts, and let's try to improve the profitability of nuclear this way. So just to make an example, in the plot, you can see that the CCG plants have staffing levels nearly 1/10 of a light water reactor. And that's the result of extensive automation supported by a rich sensor set, remote monitoring and diagnostics, an AMD center that serves multiple plants. So the plan is we're gonna make it nuclear competitive again through the optimization of the diagnostics procedure and improved online monitoring techniques. So next, please. Thank you. So the point is that we are moving towards autonomous operation, but the point that we're trying to make is that the human has a role to play in autonomous operation, because the operator is expected to be functioning at a much higher level in decision hierarchy, right? So in an under autonomous operation framework, control still needs to be transferable to the operator. So the point is that there are situations when the control gotta be transferred to the operator. So there must be provision for continuous updating of plant status, condition, and health, so that the operator situational awareness is maintained in general and in event of transfer of control. Okay, so operator still has a role to play, and diagnosis needs to ensure this situational awareness. And the basic requirements for diagnosis are the trustworthiness. So the idea is that the diagnosis gotta be consistent with physics, and the operator gotta be in the position of trusting the outcomes of the diagnostics. The explainability, so the diagnosis gotta be representing a scheme that parallels human cognition, and actionable. So the outcome of diagnosis gotta be a course of action that makes sense, that is consistent, and that is transferred to the operator with no confusion. Okay, so he knows what to do and he knows what action he gotta take. Okay, so these are the major requirements that we are trying that gotta be fulfilled to ensure this situational awareness. Next, please. Okay, so that's the plan, and but the point is that presently the operator response to events is symptom-based. Okay, so the idea is that how it works, that the operator formulates high-level hypotheses of the plant state by combining multiple sensor readings with an understanding of the laws of physics that are behind, right? So the idea is that it might be this. These are the sensor readings. So it formulates hypothesis and validates this hypothesis. The point is that this approach can hardly be implemented, right? I mean, or at the system level. Why? Because of the complex behavior of multi-component system, because of myriads of sensors, because there might be errant sensor readings, or because the sensor set are just not complete to have the big picture of what's going on. So what the point we're trying to make here is that we gotta try to automate this reasoning approach, okay? And the point is that these needs can be best met by a machine that mimics how the human processes information to draw inferences, okay? So our approach is we gotta try to develop algorithms that mimic the way human brain processes this amount of information at a higher level, you know, with the at this level of complexity, okay, for a multi-component system with myriad of sensor and this huge amount of information that is received all the time, okay? So next, please. Okay, so there are basically two schools of thought, two philosophies here. So we can either go to purely data-driven approach. Okay, we can either adopt this purely data-driven approach or a physics-based approach. Okay, or a physics-informed approach, whatever you want to call it. And the point is that the physics-based approach basically means the inclusion of domain knowledge in the statement of ML problems. And I don't have the time to get into the detail. I have 4 minutes. But the point is that the physics-based approach is going to ensure many more capabilities that are fundamental for autonomous operation. In the table, there are some of them are mentioned. And to me, one of the coolest one is, for example, let's assume that you're changing the operating points from 100% to 70%. You need a diagnostic system that understands that you're just changing the operating point. There's no fault involved. There's nothing wrong. So a purely data-driven process might lack this capability, or the capability of discriminating between components level fault and sensor level faults. So all these capabilities, I mean, physics, to the best of our knowledge, physics-based approach can ensure these capabilities, and that's the way we are going through. Next slide, please. So basically, the reasoning algorithms that we are proposing basically mimics the same thought processes an operator uses to arrive at fault diagnosis when given enough time and access to instrument readings. Okay, so the automated reasoning is a formal way of inferring the status of a system, giving a set of relationship among system variables. Okay, so as shown in the picture, the idea is that we proceed for the diagnostic with a backward chaining. Okay, so we start from the effects, so the symptoms, the sensor readings, and we get back to the cause to define and to come up with the diagnosis and figure out what the hell is going on. Okay, but then after that, the results are explained by causality, by a forward chaining inference. Okay, so that's the same way the human brain works. So let's start with the cause and let's prove to the operator that this cause, this original source of the problem of the fault is consistent with the symptoms, with the data readings. Okay, and that's the trustworthy thing that I was mentioning at the very beginning. And finally, to handle the uncertainties and the probabilities, we are using the Bayes theorem to yield probability to have a particular fault as occurred. Okay, so next. And now in this, I still have 2 minutes. In these 2 slides, I'm going to just present a couple of applications. So the point is that we've been collaborating with utilities, and we developed 2 test cases to prove with real data, with experimental data, the capabilities of this approach. So in this case, we work with this utility about the monitoring of the condition of feedwater pumps. Okay, so the system was a BWR. Okay, and the industry need was deferral of maintenance related to equipment overhaul and sensor calibration. So the plan is we wanted to monitor the condition of these components. Okay, in particular, these are pumps, feedwater pumps, and the plan is through automated reasoning with physics-informed digital twin, we want to figure out if there is a problem to the component. And when I say component, I mean the pump, the motor, the bearing. Okay, so the hydraulic part, the electrical part, or if there are problems to the sensors. Okay, and so basically we played this game. I mean, it was like a double-blind test. Okay, so the utilities provide data, and they said, okay, here's your data set. Is something going on in here? Is there a problem? And if there is a problem, what kind of problem? And is a component level or a sensor level? So we successfully diagnosed, this kind of problems, this kind of faults affecting the pump. So it was a degradation of the pump performance and the problem of calibration of the sensors. Okay, and yeah, almost done. Just a last slide, please. And in this case, it was a system level problem. So in this case, it was another utility. This time was a PWR. So we had a very complicated system. Like I think it was 40 component system with feed waters, heaters, with pumps and stuff. And basically, we played the same game. So we received these data sets, and the game was let's see if there is a degradation phenomena affecting the water heaters, or if it was a sensor level faults. And also in this case, as you can see in the plot on the bottom, basically, we diagnosed this degradation of efficiency. In that case, it was the heat transfer coefficient, that was the matrix. And basically, as you can see, once the heat transfer coefficients got outside the confidence interval, the 95 confidence interval, basically with diagnostics that yes, beyond any statistical doubt, there is a natural degradation, and we define the control action to be taken. And that's all. Thanks.
Okay. That's
sorry.
Interesting. Yeah, that's really interesting work. Thank you, Roberto. That we're looking at a lot of these similar things, so it's interesting to see your perspective on that. So thank you very much. Okay. Next is Preeti. So if she'll join us again. Thank you. Sorry for the confusion last time. So she's going to be providing us an overview on resilience-friendly features for NMAC, which I mentioned earlier. So Preeti holds a PhD in nuclear engineering from NCSU and is currently working in the development of formalized frameworks for credibility assessment of computational simulation for advanced nuclear reactors. So welcome, Dr. Antha, to this Resilience Symposium.
Hello everyone. Today's talk is focused on resilience-friendly feature of nearly autonomous management and control system. Next slide, please. So here are the contents of this presentation. I'll start off with briefly describing what is NAMAC, its architecture and workflow, then discuss requirements with respect to resilience, and then finally discuss some resilience-friendly feature of NAMAC. Next slide. So NAMAC system, as the name suggests, has been developed to support the operator ability to control the plan in case of abnormal situation and accident scenarios. Next slide, please. So this slide describes the operational workflow of the NAMAC system, where we have a scenario-based model of plan, and which consists of multi-physics system simulation as well as virtual instrumentation and control. So the sensor data is taken from the plant simulator and processed by the diagnosis element in NAMAC, which determines what is wrong with the reactor. And then based on the diagnosis, it determines what are the possible control actions. For each options, it projects the effects of the action into the future behavior of the plan and determines the consequences. And depending on each consequences, the strategy assessment block in NAMAC determines the best course of action with respect to safety, reliability, and cost. In addition to this, NAMAC also has discrepancy checker. Can you click again? Yeah, so the discrepancy checker acts as an uncertainty manager, and it takes into account situations that are beyond the scope of the NAMAC system. Next slide, please. This slide describes the NAMAC architecture, which is based on the data, knowledge, information pyramid. So at the bottom of the pyramid, we have the knowledge base. And then we have the developmental layer, which extracts the knowledge and develops different digital twin based on the requirement of the case studies. If you can click again, yeah. So the development layer extracts the useful information from the knowledge base, and it creates digital twin based on different functions. So the digital twin acts as a knowledge acquisition system to support specific functions like diagnosis, strategy planning, prognosis, and strategy assessment. And finally, all of these digital twins are assembled together into a hub to formulate the real-time operation of the NAMAC system at the operational layer. Next slide, please. Now we'll talk about the resilience. So when we talk about resilience, we can start off with the resilience of the NAMAC system. And since we use NAMAC to operate the plan, so the resilience of the plan in turn depends on the resilience of the NAMAC system. So this whole problem transforms into a hierarchical decomposition of resilience, where we had the nuclear power plant at the top, and then the NAMAC system, and then as we explore the NAMAC system, we have different NAMAC components. So it transforms into a hierarchical decomposition, and which is in turn linked with the development and assessment process itself. Next slide, please. And this slide talks about functional implementation of resilience. So when we talk about resilience, there are different attributes for resilience like reliability, robustness, and all these two components are act as a subset for resilience. So when we talk about reliability, the essential attributes is diversity and redundancy, and all of these attributes are important for different elements and components of the NAMAC system. When we talk about robustness, this is the situation where the system is operating is operating in the accident regime or situation which requires higher safety margins. So we need more coverage and extrapolation in these cases. And we talk about resilience. Resilience has reliability and robustness as sub-attribute, and additionally it requires additional attributes like agility, which requires fast action and execution, scalability, and improvability. And all of these attributes are important in the different components of the autonomous control system, which which in turn is also related to the development and assessment process. So the entire functional implementation of resilience is dependent on all of these different attributes. Next slide, please. Now we'll talk about some resilience-friendly features of the NAMAC system. So within NAMAC system, the first feature is related to the data-driven digital twin implementation. So within NAMAC, we have diagnosis and prognosis system, which have been implemented using feed-forward neural network and recurrent neural network. And this is something that provides higher learning capability, fast execution, and some degree of extrapolation capability, scalability, and as well as robustness. And some of these qualities has been demonstrated to a certain degree using some case studies, which have shown that NAMAC does possess certain degree of extrapolation capability for accident scenario involving loss of flow accident, component degradation, and sensor malfunction. Next slide, please. Another feature which adds to the resilience of NAMAC is the digital twin development and assessment process. And this feature is indirectly related to the resilience of the NAMAC system because it's more of in the developmental phase. However, it's very important because this is the stage where we identify major sources of uncertainties and try to build a more robust system. Additionally, when we talk about the architecture of NAMAC, within NAMAC, we follow a modular architecture, which provides transparency, and it is also helpful in testing different algorithms and within the workflow of the NAMAC system. The Ensemble DT and DT Hub provide diversity and redundancy in the NAMAC system. So these are some of the important features that can contribute to the resilience of the system. Next slide, please. This slide is focused on another element which is important for resilience, which is the discrepancy checker. Within NAMAC, the discrepancy checker provides real-time online uncertainty management, and it's important because it adopts the different lessons that we have learned during the digital twin development and assessment phase, and it adopts them in practice for uncertainty management during unexpected transient or situation which are beyond the scope of NAMAC DTs. So it kind of prepare NAMAC for unanticipated situation and helps in managing uncertainties. So yeah, that was all about my presentation. Thank you.
Thank you too. I appreciate that. I was really interested to see your Venn diagram on resilience versus robustness, and we've been talking about that. So it's interesting to see your approach in this work. So thanks for sharing that.
Thank you.
Okay, so now we're moving on, just running a little late. I appreciate all the presenters and trying to stay on time, so thank you. Next, I'll introduce Andre. Andre is going to be presenting our last slide for the day. So Andre Gribak is going to provide insight on support vector analysis for computational risk assessment. So you can see that right there on your screen. So Dr. Gribak is a distinguished researcher at INL, and his research areas include Bayesian inference and machine learning, reliability and soft computing in nuclear engineering, nuclear systems instrumentation and controls, prognostics and diagnostics for nuclear power plants, along with probabilistic risk assessment. Well, lots of journal articles and publications and books, and thank you, Andre, for joining us. Appreciate your time here. So please take it away.
Thank you, Craig, for introduction. And my name is Andre Gribak, and I will be presenting our project on support vector analysis for computational risk assessment, decision making and vulnerability discovery in complex systems. It's a joint project, and my co-investigator is Curtis Smith. He's also from Idaho National Laboratory. Next slide, please. Why are we doing this, and what is the goal of this project, and what are the challenges? We want to automate discovery of vulnerabilities in complex systems using machine learning and fault tree analysis. Why we want to do this? The safety of nuclear power plants and the reliability of nuclear plants are of paramount importance. And the current analysis of reliability and safety of nuclear plants is normally performed by applying probabilistic risk assessment. Probabilistic risk assessment relies on two core technologies. And one of them is fault tree analysis, and the other one is parameter estimation. And fault tree analysis is it's a technique that is mostly document different vulnerabilities found by an analyst. So you have to have an analyst who would look at the system, analyze, and come up with a fault tree and document those vulnerabilities. However, for any real system with a large number of components, that number of paths to failure is enormous, and we are not very well equipped, humans, to deal with a lot of permutations, and we all make mistakes, including logical mistakes. To look at this problem and to approach this problem, we thought that the machine learning and artificial intelligence can help. Especially, we are interested in developing tools that would help to analyze logical fallacies and logical constructs. As you know, majority of machine learning applications are focused towards forecasting and classification. But the application of machine learning and artificial intelligence to logical problems is not well developed. So that was our interest. And of course, we had applied problems in mind too, because we want to use this technology to find previously unseen issues in our systems and to reduce cost of analysis, and maybe to intelligently sample the state space of the system, so we don't have to analyze the whole number of different permutations. Next slide, please. So to demonstrate, I am showing a very simple system, extremely simple system, which is a water source, and it has two pumps, and has a valve, and it has a reactor. And the top event for this system would be the lack of flow, no water flow to the reactor. No water flow can happen if the valve C failed or both pumps, A and B pumps, failed. And to represent this configuration, we can use a fault tree, which is shown on this slide. And we can see that the pumps A and B, they're connected through logical gate AND. They both need to fail, and the C is connected through with them through logical gate OR. Next slide. And this has been developed. The original tree can be developed by the analyst. However, what if analyst made a mistake in terms of logic of the diagram? And what if instead of AND we have OR? How this could happen? Well, imagine that we overlooked a common cause failure. We were not aware of common cause failure, and the failure of a pump A or failure of pump B essentially implies the failure of another pump. And in this case, the gate would be OR. So, and of course, and we would like to be aware of this situation and how much it changes our analysis. Next slide. And for the current system, it's very simple. We can only come up with 4 different configurations, and by changing actually the gates randomly. It's called fault tree rewiring. And in this case, we'll get 4 different configurations, and we have three input variables. Next slide. Of course, each configuration have its own truth table. And what's important here is that notice that the truth table, which has two end in it, the bottom truth table has the lowest truth density. It means that it represents the most reliable configuration. The truth density is very low, and the truth table, which has two or, the second from the top, has the highest truth density. It's the least reliable configuration. Next slide. To analyze these the logical constructs and the fault trees, we decided to look at the support vector machines. Support vector machines is a well-developed tool, but it does require to represent inputs as numerical vectors, and it's very well equipped for the binary classification, which is exactly our goal, because we want to classify the events between failure and non-failure. Next slide. The idea of support vector machines is to do classification based on the hyperplane. For example, if you have two classes and those two classes can be described by two features, x1 and x2, then you can use a hyperplane, the blue one, to separate those two classes. Of course, simply finding the hyperplane is not enough. Next slide. Because that hyperplane is not unique, as this and as the left plot shows, you can draw, for example, two hyperplanes, and they both will classify the trained data correctly. However, if you try to apply those two hyperplanes to the new test data, then one of them will be better than the other. Next slide. So support vector machines are using the quadratic optimization to find the so-called optimal hyperplane, and the optimal hyperplane is the hyperplane that is on the furthest distance from the patterns in both classes. Like on this slide, it's shown in yellow. So, and the optimal hyperplane has a very nice property, is that if your future data will come from the same distribution as your training data, then this will minimize the error on the test data, on the future data, which what we would like to achieve, and that's what we want to accomplish. Next slide. However, we are especially interested not even in classification, but in the so-called support vectors that support vector machines find. These support vectors are the most important data points in the state space which are necessary for classification. Essentially, they are most information rich, and they lies on the border of two classes. And as you can see, say in this plot, it's just a small number of the overall number of training patterns. So looking at the support vectors, you can actually analyze what patterns are, what data points are important to classify. And as I said, they are information rich, and essentially they are the only one that matters for classification. You can change other points, and the hyperplane will not change. Next slide. So going back to our two pumps example, what we did, we represented the system as a 5-component vector, and each component is represented by binary variable, and the OR operation is coded as 1, and AND operation is coded as 0. And as you can see in the table, since it's 2 to the power of 5, we only have 32 different configurations. So when we take these configurations and we train the support vector machines on those configurations using the response or top event variable, which is T, and we have two classes, of course, 0 or 1, failure or non-failure. So we train support vector machines on those configurations, and we look at configurations which are found as support vectors. Support vector machines is a very stable algorithm. It minimizes the quadratic minimization problem. However, it does have a number of hyperparameters. And when you start optimizing hyperparameters, it will produce slightly different results. Next slide. And so what we did, we trained support vector machines 100 times with a slightly different hyperparameter optimization. And each time we get a slightly different classification. However, what's important here is that that histogram or a bar plot, as you can see, on the y-axis you have the counts, and on the x-axis you have a configuration. And you can see that actually the configurations can be very efficiently split into two classes. One class is the configurations that are always selected as support vectors. It's 100 times, we did 100 times, and they were always selected as support vectors. And the other ones, which are almost never selected, and either never or almost never selected as support vectors. So you have two classes, and we are interested only in those that are always selected as support vectors, because they are important to classify our data. And in this case, as you can see, there is about 50% of the configurations that are always selected as a support vector. However, next slide. A very attractive feature of the support vector machines is that as the number of configurations goes up, actually the number of support vectors is increasing in percentage of the support vectors are increasing. For example, this is a much more complex Boolean expression, and it has a 131,072 configurations. And as you can see, if we use a certain number of data points from those configurations, then the percentage of the total number of data points which are found as support vectors is less than 1%, which is very small number, and that less than 1% can be analyzed further. Next slide. Will be my last slide. So this work actually demonstrated to us that we can use support vector machines to classify Boolean fault trees into two classes, and we found out that the number of support vectors is just a fraction of the percent, and that number is much smaller and can be further scrutinized for vulnerabilities. And we plan to publish these results in conference proceedings and in journal paper. That's it.
Okay, Andrei, thank you so much. Appreciate that. Appreciate everybody that stuck with us. We went over a little bit, so appreciate you spending a couple extra minutes with us. And thanks, Andrei, and thanks all the presenters that took their time to share their work with us. We'll be announcing, I will be sending out the slides for everybody. We'll send a link out so everybody can see these slides and contact information of the presenters so you can follow up with them directly as well. So again, thanks to the presenters and all the people that helped pull this together. Appreciate everybody attending. We'll send out an announcement for the Symposium 7. We've already got quite a few people interested in presenting out more information. If you are interested, please feel free to contact me as well. I'd be happy to discuss that. So with that, we'll end it. Thank you very much.